Hello everybody, welcome to another devlog. So we're just going to recap on what we've been doing in the past 3 weeks worth of streams. We've been working on this top level bounding volume hierarchy, which allows us to have instances of these meshes or ellipsoid 3D models. And then after that, I would like to give a quick overview of the plan that I have for the next 4 to 8 months, which will allow us to basically build these custom ellipsoid models in the game and other things as well to do with the game technology. So let's get into it. Right, so if you remember from the last devlog, we basically had a single object, which is a bottom level BVH made of ellipsoids, and each leaf node was an ellipsoid, and as you went up the tree, those parent nodes wrapped a bounding volume around those leaf nodes and so on. So you had a whole tree of this, what's known as a bounding volume hierarchy, so we could accelerate the ray tracing. So this is a bounding volume hierarchy where it's just got 4 leaf nodes, but instead of each leaf node being an ellipsoid, it is instead an instance of a bottom level bounding volume hierarchy. So when we ray trace against these leaf nodes and we hit one, instead of rendering an ellipsoid, instead we swap out to the bounding volume hierarchy for that instance, and then we ray trace down this bounding volume hierarchy until we hit all the leaf nodes that we're going to hit, and then we traverse back up to our top level BVH and carry on there. Right, so what we're looking at here is a 5x5 grid of instances where each instance is that 8x8 set of ellipsoids, and it kind of looks like water, which looks quite nice, especially with that PBR. So maybe we'll use something like this in the game, or it's quite pleasing to the eyes, I think. So the tree would look something like this. It's not actually this. This is just the debug visualization of a tree, where each leaf node in this would be an instance of that. It would just be this instance thing, and it has a link to the bottom level BVH and some transform data, so it translates it from local space into world space, so it can have stuff like rotation, scaling, and translation. All right, so this is our data shared between the CPU and GPU. So here is our BVH reference. So this is a way to reference to a whole BVH tree by pointing to the base node of the BVH. So this is actually only 16 bits, but because we're on the GPU, we've kind of got to make it 32 bits, but it means we can pack it into 16 bits when we're on the GPU. So how we get into 16 bits is that it actually can address 24 bits worth of nodes, but we align our BVH to this BVH alloc align. And if we just quickly take a look at that, that ends up being aligned to 256 nodes. So when in our custom BVH node allocator, we align every allocation to 256 nodes. And so we waste a bit of memory there, but it means we can basically shift it to the right by 8 and then just keep it in 16 bits. And then when we want to get the actual base node back out, we shift it to the left. And then we've, got some savings there if we store it a lot of the time. So the other sort of ref that we have, or reference, which again fits into 16 bits, is this BVH child nodes reference. So this is a relative index from that base node index of the BVH ref. So we use this in the traversal code, and it uses some similar tricks, right? It only points to the first set of 4 nodes, and that is aligned to 4 nodes all the time. So it means what we can do is we can address probably about 14 bits worth of nodes. Wait, 16 bits worth of nodes, yep. And then in the low bits, we store the count. So the number of nodes, the number of siblings, also the number of children that we're pointing to, basically. So those store in the low 2 bits. there by taking the number 1, 2, 3, or 4, taking away 1 and packing it into the first 2 bits. And then we unpack it like so. When we build the BVH, we used to just have this sort of BVH build ellipsoid, and this is our leaf node, and we just create an array of these BVH ellipsoid, give it to the BVH API, and that will just run a bunch of compute shaders and build a tree on the GPU. But the way the instance one works is basically the same way. We have our center position, our half dims, and our world from local rotation as a quaternion. But instead of a material index, we have a BVH reference. So the only thing that's different between these two is this one's an ellipsoid and this one is actually an axis line bounding box, I think. I still got to settle on that. But yeah, that's for future me to solve a bit. Right, so this is that BVH node structure. I think in the previous devlog I had this at 16 bytes per node, which is really nice because I could pack 4 of them into a single 64 byte cache line. But I had sort of some precision issues and I wanted to just get it working and deal with the packing later, but leave the door open for it. So I just decided to very loosely pack it into 32 bytes of information. So there's 8 4-byte integers that we're just packing the XYZ component of the center position, half dimensions, and space from local rotation into 16 bits of into 16 bits of data. There is the 16 bits used in this word 7, right? And it switches on the node type, which is stored here in word 5. Again, the packing is very poor, but anyway. For a parent node, these 16 bits represent a BVH child node reference, so we can basically just offset relative from that base node index of the BVH reference, right? Or the current tree that we're traversing, basically. But if we hit a leaf node and we're in a top level, we get a BVH reference, so we can swap out the whole BVH tree to traverse a bottom level BVH instead. But if we hit a bottom level leaf, we've actually hit an ellipsoid, so we need to have the material so we can do the whole PBR shading, right? So effectively this BVH node can support those, you know, either a parent node or the top level leaf, which is an instance, right? Or a bottom level leaf, which is a ellipsoid. So another key thing to take away is that when we hit that top level leaf node, right, what we've hit, like we have that BVH reference here, but that transform information is all part of the bounding ellipsoid. So we're able to sort of translate into the local space just using this information alone. And another key thing to take away is that the top level BVH is in world space and the bottom level BVHs are in the local space of the object, right? As I mentioned earlier, that, you know, we can basically make instances. The performance isn't really the best, but it's fine because in where we're going to next is I just want to be able to make a basic level and we can deal with better rendering later. I just need a way to be able to create content first. So I quickly just want to show you a couple of papers that I'm inspired by, so next time I'll probably be doing something like this and the types of problems that we have to yet solve. Okay, so the current problem with our BVH node structure has got a kind of bit of a wider node where we have 4 children, and I've tried to pack it down because I'm aware of, like, I want to pack things into cache lines, right, and reduce the amount of memory I'm reading back and how much cache is being used up by these BVH nodes. And I was looking around, and there's another paper that actually solves this, and it solves another problem that I'm also having as well. So this one's called Efficient Incoherent Ray Traversal on GPUs through Compressed Wide BVHs, and this one uses 8 wide nodes with 8 children, basically. and it packs them into 128 bytes. So that's 2 cache lines for 8 children. So that gets the same sort of ratio as I was hoping. I also have a problem of when I am traversing down the tree, how do I pick the closest node so I can find the closest ray-verse ellipsoid first, so I can basically get an opaque hit and avoid searching the back end of the tree. This paper answers both of those questions, so I'd like to try and implement this one, or future Henry will, after we've done all this work, which we'll talk about in a bit. Right, so that does it for Devlog 16. The days are day 140 to day 148 if you're interested in seeing the live recordings. These will include stuff such as making the custom BVH node allocator on CPU, and also making the whole BVH API. So if you're interested in seeing that stuff, which I couldn't cover today unfortunately, that is all on the VOD channel here. Also a Twitch channel where you can catch me live Tuesday, Thursday, Sunday, and there's a Discord if you want to come and hang out in the meantime. And if you're interested in getting source code access, if you support via Twitch or Ko-Fi, there's ways to get access to the GitLab source code. When you subscribe, you can go onto the Discord, and it has all the instructions there. Thank you so much, guys. See you in the next one.